It always comes across as really loud. Anything? Okay, well, let's head back to this part. Get out of the mail there. And come back to, where did my Adobe thing go to? I was looking at it. There it is. So first of all, let's take a look at the scatter plot. And what I want to do is to have ourselves think about this as a scatter plot again, and keep in mind what it is a regression line is doing when it fits data through some scatter plots. Specifically, a regression line is going to minimize the distance between an observed data point and the regression line. So my point is, if I add in random error, say I take this data point and I give a person a bonus point that they don't deserve, and I take this data point and I subtract a point that they don't deserve, none of that is going to change the slope of this line. However, if I take the X value and I take this individual and I subtract a point on their X value and this individual and add a point on their X value, that's going to change the errors of prediction. And it's also going to change the slope of the line. So for example, this individual is being moved over here. They didn't have much error at all in their original version, and I added a point to it. Well, now they've got some error going on here, if you can see my mouse. And similarly, this individual who had a value here, and I subtract a point from them, well, now they're over here. They have a very large point. And so the line is going to change. Now, to be clear about that, it's what I'm doing when I increase error on Y. I am going to change the standardized coefficient because I'm changing the variance in Y. But the thing that I'm not changing is the unstandardized regression weight. The same line is going to go through this. And when I change this up, it's not, it's not going to. Okay, so that was a little bit of cobweb clearing. I got my hands out today. I'm doing a lot of gesturing, but when I did it the last time, it seemed like, here's this picture, we all know what it means, and I moved on, but there was a discussion. Let's move down to vector land here. So when I have an X variable that has measurement error in it, I'm going to be talking about a vector that's shorter. So unadjusted for measurement error, the length of this line might not be 1. The length of this line might be something larger. It might go all the way over to here. And because of that, when I multiply the original X variable by a number, I don't need as big of a multiplier to get to this point underneath Y. If I have only true score variance going on, well, that's a shorter line. And I'm going to need more of a number to multiply by that to come out to this point. So it kind of deals with multiplying vectors. And in the case of a single predictor, Y, adjusting, starting out with a vector that's only true score variance is different than starting out with a vector that's all of the observed variance. The other thing that I remembered is, just to repeat, and maybe there are some questions about it, reliability is the proportion of variance that is due to the true score divided by the observed variance, or another way of saying that, divided by true score plus error. And that is also known as the intra-class correlation coefficient. If you take multivariate psych, or if you had me for the GLM class, we also talk about how that number represents a correlation coefficient. But that's why it gets the name of an intraclass correlation coefficient. But for now, for this class, you just need to know it goes from 0 to 1, and it's the proportion of variance due to the true score. So that was a little bit of conversation. Are there reactions? I didn't freeze. All right. So I tried to think of some small diagrams that would help us think about building a structural model. So let me bop back to Onyx here and talk a little bit about visually what is going on when we're doing a single regression, single predictor regression, and what we're doing when we correct for attenuation. So in our previous work, for example, we talked about predicting wave 2 based on wave 1, and we drew a line and we freed, oops, and we, excuse me, there, and we freed that parameter. And this is the path diagram that corresponds to a single predictor regression. It is a statement about 3 things: the variance of time 1, the variance of time 2, and the covariance. And when I draw a just identified path diagram, I need to have three parameters in my model. And there they are. Now, when I correct for attenuation, notice it's the same darn picture. It's just that, oops, this is gone, and I'm now talking about a variable I don't have. And I can again draw this diagram. Well, there's a problem here, especially if I free this parameter. In my data, I have only one variable. I have only one variance. I can estimate only one parameter. So I'm going to have to do some fixing here. Well, very frequently, one of the nice things about structural equation modeling is that whenever a sling joins an exogenous variable with variance 1, that sling is a correlation. So maybe one thing I want to do is to fix this to 1. Well, I still got 2 parameters. This is still a problem. And what I can do now is to come downstairs here and fix this number to some numerical value. Well, that's the diagram on the left in the handout. So if I say take the reliability of 0.5 and multiply it by the observed variance, let's just say the observed variance was 50, I might fix this at 25. And this now represents, it just has one free parameter in it. It's the summary of the data. This thing is going to have as its interpretation my estimate of the standard deviation of the true score variance. Okay, so this seemed to be kind of a big aha moment in office hours. I thought, well, if I can do it once, I can do it some more times in front of the whole class. But that's all there is to this. Are there reactions or questions? So it's just the same darn picture, but whoops, I forgot to have my predictor variable. Actually, that's all factor analysis is. Okay. Now, the funny thing about teaching, Pat King, who just retired this past year at Michigan State, my advisor in graduate school at Iowa, said, you know, when you ask a question, be sure and wait a bit, because often people will say, are there any questions? Wait 2 seconds and then head on. And people frequently don't ask questions then. All right, so let's go to the third thing, and there'll be some summary comments. Let me delete that and say, here I've got a picture. And one of them is a 3-factor model. So this is a factor analysis. And the next chapter, after we're done with this correction for attenuation business, we'll get into factors formally. But think of it as a picture. What we are looking at here are exactly the same 3 one predictor models. I just don't have my X variable here, but I'm predicting WIS1 from that, I'm predicting WIS2, and I'm predicting WIS3. And that's the way to think about it. And the question was, oh, gee, you know what? When I was doing other models, for example, I might try to look at the correlation between time 2 and time 3, adjusting for time 1. And I drew the picture that looks like this. This is a diagram that corresponds to an estimate of the partial correlation, between time 2 and time 3 adjusted for time 1. And the question was, well, gee, in this model, you had a correlation between these 2 error terms. And in this model, you don't. Should I maybe be also adding some correlations here? Well, 2 parts to that. Darn good question and great evidence of looking across models and saying, how is this picture different than that? And as an answer, in the general case, you could well explore whether there are some correlations going on. But upstairs in this 3 indicator model, we can't do that. We are in the deviation score matrix. We are looking at variances and covariances. And we must always count how many parameters are in this model and compare that to the number of elements, free elements, in the variance covariance matrix. So I've got 3 variables here. That will be 3 variances, 2 covariances involving WIS1, and 1 covariance involving 2 and 3. So there's 6. Well, in this diagram now, I have 1, 2, 3, 4, 5, 6 free parameters. If I wanted, even if I wanted to, I can't draw a correlation between these. So, is that okay?
Actually, can you repeat that? I think I've always been a little bit confused about identifying models that way, like making sure that the number of parameters matches what we have, what we can do with what we have.
So, for example, you can't, all right, so in the case of variances and covariances, I can't have more parameters than I have elements of the variance covariance matrix if I'm looking at the deviation score matrix. I can't have, if I'm looking at the adjoint sums of squares and cross products matrix, I can't have more arrows coming out of the column of 1s that are free than I have manifest variables. You know, not to worry about this if this is a little fuzzy, because the next chapter where we formally get into confirmatory factor models, I will go through this in hammer and tongs and talk about this is only one of the many ways that your models can go wrong. But right now, given that your official expertise is, I know what analysis of variance is, and I know what regression is, and I know what analysis of covariance is, all that good stuff. All of those diagrams have just as many parameters in them as you have elements of the variance covariance matrix or average sums of squares and cross products matrix.
That helps, thank you.
Great. See, you got to come to office hours, folks, or you got to talk more in class. So allow me to come back to, this is so strange. I keep wondering where my goes to. this allows us to explore some small diagrams that are also kind of variants of familiar themes. So I hand waved a little bit about this, but sometimes we are interested in estimating the correlation between two constructs. Episode from my own life, my federal grants were in the area of reflective judgment, and there's another, it was an interview measure of how you think critically in graduate school, mostly, and some in undergraduate. And there are other measures out there called critical thinking tests that are objectively multiple choice tests. And I tried to publish my article and said, look, the correlation is not great between these two, they're separate constructs. And reviewers came back and said, well, you would expect them not to correlate perfectly because there's measurement error involved. And happily, I ran the model that we're looking at here on the left and showed that even if you adjust for measurement error, there's still a less than perfect correlation. What we're looking at here is an estimate of the correlation between two variables, adjusting both of them for measurement error. So as you can see down here, the underlines denote things that I fixed. So in this study, the standard deviation of ACT English is 3.86, and the standard deviation of the alcohol quantity frequency measure is 11.93. And 1 minus the reliability of the ACT English score is 0.15, and 1 minus the reliability of the alcohol variable is 0.22. So I specified a structural model with these 4 parameters fixed. Upstairs, I fixed the variance of the latent variable to be 1, and I freely estimated these 3 parameters. To repeat what I said before, this number represents an estimate of the standard deviation of the true score of ACT, and this represents an estimate of the standard deviation of the true score of alcohol. Oh, okay, somebody just read it back in. And this number represents an estimate of the correlation between ACT and alcohol quantity frequency, adjusted for the effects of measurement error. And that's a different number than you would have if you just observed the raw correlation. In other words, this number is going to be larger in absolute magnitude than the raw correlation you would observe. So again, this is a single predictor regression model. It's just that we forgot to have an X variable. And this is a single predictor regression model. And this is, like Rod Serling says in The Twilight Zone, submitted for your consideration. You will see people do this in articles. And this is the gist of what's going on. Similarly, I can also adjust, I can conduct an estimate of a partial correlation, adjusting for the effect of a third variable, where everybody's been adjusted for unreliability. Now, this is ugly. People go, oh my gosh, how would I ever remember this? But what I want you to look in on is to look at a diagram and see where the little puzzle pieces, the little tinker toy blocks are that connect things. Well, what we have here, let's start up in the middle. What we have here is a correction for attenuation for ACT. So this is the standard deviation of ACT. This is 1 minus alpha. This is free. This variance is fixed at 1. Similarly, for GPA and alcohol quantity frequency, these are single predictor regressions. Correction for attenuation formulae. And now what's going on up here? Well, if these circles were squares, it would be a little bit easier for you to identify this as a partial correlation. It's been flipped upside down. This is my third variable correcting for each of these two things. This is the an estimate of the standard deviation of GPA adjusted for ACT, and the same thing for alcohol adjusted for ACT. This is fixed at 1, this is fixed at 1. This is therefore a correlation coefficient adjusted for the effects. Now, in truth, you don't often see this done, but it's given to you as an example of how you snap in the pieces. Because in your particular research situation, you're going to have different variables and different numbers of variables. You may want to adjust for more than one predictor. And if you wish to do a standardized two-variable regression, this is the diagram based on a regression model. That's just there for a pattern. So I want to, take any questions that are present, but I now want to pull the rug out from under you about the relative value of correcting for attenuation. In summary, we correct for attenuation in structural equation models when we can't do anything else. So for example, if I have in my study only one measure of verbal ability, and it happens to be a WISC vocabulary score, and I have some information on the reliability coefficients, well, that's all I can do is correct for attenuation and snap that corrected for attenuation part into my larger model. However, there's a problem. Coefficient alpha is a lower bound on true reliability. That is, if I do my study and I calculate a coefficient alpha of 0.8, the actual reliability is likely higher. And in the case of coming up here and just looking at this question, this number then should not be 0.15. It should probably be something closer to 0.10, for example, 1 minus alpha. In other words, my estimate is a bigger number than I ought to have for reliability. Therefore, because I have a number that's too big down here, I'm going to overestimate what this number is up here. So my being conservative about reliability, which classical test theory people say, oh, well, I'm conservative, look at me, in the context of a structural model starts to be problematic. And the other issue that is a problem for us is in the context of a two predictor regression equation. Let me just close this model out and open up something else here. In the context of a two predictor regression equation like this, when I correct for attenuation, it's unclear as to whether I'm going to estimate too large of a correlation between my predictor variables, or whether I'm going to estimate too large of a regression weight. There's a trade-off. In other words, that if I adjust WISC1 and WISC2 for measurement error, maybe I'm going to make this covariance bigger than it ought to be. And because that's bigger than it ought to be, these regression weights are going to be smaller than they ought to be. Or I'm not going to be affecting this covariance so much, and I'm going to be getting inaccurate estimates of the regression weights. So the fact that classical test theory doesn't give us a good number is a problem. And this is why, people like Lynn Cooper would run studies and go in and look at varieties of scenarios for reliability just to understand better what parameters are most affected by the reliability assumption. Now, upstairs here, not to spoil the surprise, but to build toward the next chapter, upstairs here, I made no corrections for attenuation, but I am able to do my regression weights here, and there's no overestimating or underestimating of the proportion of variance in a variable due to error. So this is one of the talking points for why confirmatory factor analysis is a superior strategy to correcting for attenuation. The problem is that you're going to have multiple indicators of the construct that you're looking at. So in this whisk example, if I wanted to not correct for attenuation, I might need the individual items of the whisk score and make that a factor model, and in that way estimate the true score variance of the model. And this is a heuristic. We will get into the guts of this in the next chapter, but that's my conclusion for that part of the handout. So I would like to spend our second half, introducing you to confirmatory factor analysis. And here is where we will be talking about what a factor model looks like, how we use the tracing rules to generate a predicted variance covariance matrix for that model, and how to identify the model. And up to this point, we've been talking about what I term logical identification. That is, just count how many parameters are in the model. But there are other identification issues that we need to get to. And we will also get into the guts of exactly how it is that our structural modeling programs are coming up with these numbers. Now, some of this involves a little bit of calculus. Some of you people might not want to admit it, but you've had some calculus, so this will provide you with that grounding. If you haven't had calculus, that's fine. I can sort of hand wave explain what's going on, so you have the awareness of a critical consumer of the technique. And then we'll talk about different ways of the different loss functions that are involved in structural models. Don't be scared by the term. So it's always good to start with an example. And here is one example drawn from a data set I've been playing with for quite some time. Here are 6 items that all ask college students about in terms of their drinking behavior. And that's going to produce the following variance covariance matrix. Notice the variances are on the diagonal and the covariances are on the off diagonal. Table runs for more than one page. This corresponds to the following correlation matrix. So when I just sit down with Onyx and I draw the diagram, or Levon or Amos or whatever your preferred platform is, this is the diagram that I draw. And it's, as I said before, we can think about this as 5 one-predictor regressions where I forgot to have the X variable. And I can use the tracing rules to say what each of these variables are in terms of the variances and covariances of the data. Now, if we were in the face-to-face world, I would have someone come up to the class and, point and make the trips, but we'll do it slowly here. What does this diagram say about the variance of 3-month alcohol use? Well, it's going to be all the trips that start and end here. So, oh, I have a chat comment. Oh, apologies, I didn't see the note. Okay. So I'm going to start out here and come back. So that's going to be 2.36 times 1 times 2.36 plus 3.38. And those numbers taken together are going to be my estimate of 3-month alcohol use. 8.956. Now, if you're sitting down doing the calculator, if you've got your calculator on the side and you're verifying that, you're not going to get exactly that number. We'll talk about that in a moment. It's going to be close, but it's not going to be exact. Second thing, what does this diagram say about the covariances present in the data? Well, so for example, that would be 2.36 times 1 times 0.89. And that's all the little trips that my little car can go, starting out from here and ending up here, or starting out down here and ending up over there. So to rehearse what the frequent mistakes are, traveling from alcohol use to this one does not mean 3.38 times 2.36, because after I have taken a sling, I can't go in a backward arrow. So to me, the rest of the variances and covariances in this diagram should be pretty obvious. The variance of 5 plus drinks is 0.89 squared plus 0.44 and so forth. Now, why are we not getting exactly the numbers that we found in our variance covariance matrix? Well, let's come upstairs and count how many parameters we have going on here. I have 5 variances plus 4 covariances involving 5 plus drinks plus 3 plus 2 plus 1 covariances involving typical drinks on Saturday. So if you're thinking about a lazy way to do this, the formula is always the number of variables plus 1 times the number of variables in your study divided by 2. So 6 times 5 is 30, divided by 2 is 15. In this diagram, let's count. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 parameters. So I have fewer parameters in this model than I have unique elements of the variance covariance matrix. In order to be useful, a scientific model must be a lie. In other words, I'm getting away describing reality here, where reality is defined as all the variances and covariances, by invoking fewer parameters. And if that model fits well, I'm going to say this model has parsimony, that it explains a larger phenomenon via a smaller number of processes. Is that okay?
Can you repeat the formula that you say number
Yes.
of variables times something? I just missed
Right,
it.
okay. Number of variables plus 1 times the number of variables divided by 2. So in this case, we have 5 manifest variables. So it's going to be 6 times 5 is 30, divided by 2 is 15.
So can you also repeat one more time what that numbers gives us? This formula give us. I just lost my attention. So if you can repeat the reason why we used that formula.
The reason why what?
So, what does this formula tell us? The number of variable plus 1 times.
It helps us count the number of unique elements of the variance covariance matrix.
Oh, okay.
In this case, it's 5 plus 4 plus 3 plus 2 plus 1, if I'm sort of counting this diagonal.
Okay.
And just for the heck of it, if you're ever counting the number of unique correlations, and this doesn't come up much, that's going to be the number of variables times the number of variables minus 1 divided by 2. So in this case, that would be 5 times 4 is 20 divided by 2 is 10. There are 10 unique correlations down here.
Okay. Thank you.
Yeah, or if you're kind of tying back to other things you may have had in probability, it's n plus 1 choose 2 in terms of combinatorial. But, okay.
Question, Professor.
Yes, sir.
So you mentioned about parsimony, where the number of parameters equals to number of elements,
Yes.
and which is it is just identified.
Sorry, it faded out a little bit again. Where do I see
So
this?
when it is equal, then it is just identified.
Yes. Mhm.
And when the parameter number is more than higher than number of elements, then it's over identified.
Right.
And
Right.
so which one is preferable? Which is it parsimonial, where
Ah,
the number are similar, or over identified?
okay. So this is a conceptual difference between these statistical models and other ones you have had. Because in every model where you're talking about an equal number of parameters, from a structural equation modeling perspective, confirmatory factor model perspective, that's not a parsimonious model. Because in structural equation modeling or confirmatory factor analysis, I'm trying to explain a lot of phenomena, a lot of variances and covariances with very few numbers. And so it is good if I can talk about just a few numbers in here, and this will do a really good job of replicating or giving me numbers that are very close to what I observe in the data. So from a structural modeling perspective, that's a good thing. And that reminds me, you had said, well, what happens when my likelihood ratio test is significant, or when my chi-square model is even? If you're looking at a standalone model, and we're looking at this factor model, and we have a chi-square that is not significant, that's good. Because that means this small set of numbers has done a very good job of explaining the entire variance covariance matrix. So when you are reading an article, and I get a few of them every year, where someone says, I did a structural equation modeling, and the chi-square for my model is 2000, and p is less than 0.001, isn't that great? It's not. In confirmatory factor analysis, you're trying to find a chi-square that is not significant, because the chi-square being significant tells you that your model assumptions or your model are wrong.
So p-value should be large then.
Yes. In other words, if I'm just looking at my one model, that chi-square should be absolutely, the smallest number it can be. So just to show a picture, let's come back and do a quickie little Onyx thing. Let's add variable 4 to this and draw a model there and free that parameter. Now I'm doing a confirmatory factor model. Well, inside of here, I'll bring it into the middle. Here's my chi-square with 6 degrees of freedom, and it's 830. In other words, that's a bad thing in this model. So a single factor is not explaining these data well. What you want to see is a chi-square that's not significant. And we'll get into the guts of the chi-square and what a big number means and small numbers and how degrees of freedom comes in, but we'll talk to that later.
Will you also describe why the chi-square is the test for this? Like, what's the rationale?
Oh, I'll give that to you because you're old enough now to know where little chi-square statistics come from. But here we go. So we'll get into that. But the funny thing is, one of the things I think that's a difficulty is, and maybe one of the things for me to teach this course is, in statistics classes, it's all about the mathematical rigor and we must follow from our axioms and so forth. To pick this up, it's a little like painting or playing a game, and you'll see some pictures and go, oh, okay. And then what I want to zoom in more detail on what those pictures are later. But for now, here's a picture, here's kind of what it's doing. And the same course as we can look at an explanation of a variance covariance matrix, we can also look at a factor model based on a correlation matrix. Same old thing, same tracing rules. The variance of alcohol use in standardized metric is going to add up to be the number 1, right? Because it's standardized. That's going to be 0.79 squared plus 0.38. What does this diagram say about the correlation between these two variables? Well, it's going to be 0.79 times 0.8. Ought to be pretty darn close to 0.64. Let's come upstairs and look at it. Yeah, 0.645. So, it's the same darn thing. It's just that all of these numbers are going to add up to be variance of 1. This is always going to be 1 minus the square of that. And if you want, you can always calculate the proportion of variance for this variable given the unstandardized solution. Well, how do we do that? Well, the same way as we did it for corrections for attenuation. The total variance of this variable is 2.36 squared plus 338. That's the denominator. And the numerator is going to be 2.36 squared. And that's going to give me the same number as I would have if I would take 0.79 and square it in the first place. Now, the little thought bubble, usually if this is in class and I'm looking at people and they have their videos turned on, it's like I get a lot of, well, who cares? But those are the relationships between the two diagrams. So I have just a few minutes. I'm going to start here and we'll pick it up on Monday. But often when you're playing with factor analysis, you're going to have a really big diagram. Now, yes, you can in Onyx sit down and draw things forever, or in Amos, but it might get to be very uncomfortable. And some of you will be doing behavior genetics, and you'll have to think about your data in matrix form there. And all of you are going to be researchers in the area reading in structural equation modeling after this, because you're going to be the expert. And the language of structural equation modeling revolves around a few very simple matrix algebra formulae. And equation 8.1 is one that you will see a lot. And let me explain to you the mystical meaning of all these words. Sigma is the predicted variance covariance matrix, because Greek sigma is the letter for S, and S is the word we often use to describe variances and covariances. And the pattern that you see in here is lambda, phi, lambda transpose. And lambda contains your factor loadings. Phi is the variance covariance matrix of latent variables. And lambda transpose is the transpose of the factor loadings. Theta E, or theta epsilon, depending on your notation, is the variance covariance matrix of the error terms. So in the little example we have here, and that's what I love about being able to make this book, is I don't care how many pages it takes, I can draw up the example for you. We'll take our diagram here and say the predicted variance covariance matrix is going to be this times 1 times this plus this. And you can copy and paste this into Excel and verify that, but if you do this matrix algebra, you're going to get this predicted covariance matrix out. Well, there it is, all done for you at once. You can do it once in Excel. You don't have to sit down and look at the diagram and do it all by hand. I do them all by hand when I'm sitting in doctoral defenses and I'm bored. So make your dissertation defenses exciting, darlings, or I'll start doing tracing rules. So in one fell swoop, I can do all of these calculations to get me the predicted variance covariance matrix. In like form, I can use the standardized solution to get a predicted correlation matrix. And this bears now on the issue of model parsimony. I've got fewer parameters than there are elements in here. All right, so this is an absolutely great time for me to stop, because we will now proceed to model identification and what you need in order to have a model that runs. And the reason that you care about this is that statistical software, don't know nothing about birth and babies. It just crunches numbers for you. And it may be the case in your structural modeling program that the model is not identified even though you correctly counted the parameters, right? So let's stop there. And I will do office hours and handle any other questions. And I will see you on Monday. And if you are reading ahead, this is the part that, the next few parts that you can read ahead on.